So we're not going to look at bound fluids anymore. We're going to look at the vast unbound fluids in the universe, the whole concept of flow over immersed bodies. And so this will come up in quite a few situations, and the two biggest ones that we'll look at is we'll look at unbound fluids in air and in water. So just give a couple of examples. So in the air, we'd be looking at something like an airplane. As it pushes through the air, we would be looking at cars, because even though they roll on the ground, they're still pushing through the air. A really interesting one would be a snowflake, because of the way they fall through the sky. Snowflakes and raindrops are fascinating, because there's a lot of stuff going on, because as they're falling, their mass and acceleration are changing, so Newton's equation gets really interesting. And the last one would be ships. Because everything above the waterline is exposed to air and you're pushing through it. And so in the water, fish are a big example. Submarine is completely bound by the fluids. It is, that's an R. Since it is pushing through, it's got water all over the hull. And speaking of water and hulls, ships below the waterline. So you have a couple of different interactions that are going on with a ship that makes it interesting, because you have composite forces, because you're dealing with both the ship touching the water, the ship touching the air, and then you have that interface. Remember, we have that free surface between the two. That has an interaction too, which we'll talk about a little bit later. So typically when we're dealing with fluids, there's a couple of things to note. Is the difference between what we call local velocity and free stream velocity. So we've already talked that Vx, Vy, and Vz in fluids, we'll talk about U, V, and W. But we do have this concept of local and free stream. So local velocities, these are the ones that are going to be close to the body. These are actually going to, and we'll talk about this when we talk about boundary layer, local velocities are the velocities that are close enough to the body, they're affected by friction. And so that's going to be an important distinction later on. And then what we have the free stream velocity. This is far away from the body. And so this is far away from the body. This is the fluid as it's not being affected by the body at all. It's so far away it doesn't matter. Now the reason this is important is local velocities will use lowercase letters. U, V, W. We'll try to remember to put the tails on the V and the W to help distinguish them. Free stream velocities will be capital. Capital U, capital V, capital W. And I will try to remember to put the little bars at the top to distinguish between capital and lowercase, because it is a very important distinction between the two. Now, the next thing that we want to talk about is we have two types of bodies that we talk about when we're dealing with flow over immersed bodies. And the first one is what we'll call a streamlined body. You might remember we talked about streamlines a little bit earlier in the class. And so what is a streamlined body definition? It has little effect on the fluid around it. Now this should make sense because this is, streamlines are showing how the fluid flow flows. Little effect on the surrounding fluid. Now some examples of this would be an airfoil, a race car, the spoilers on race cars. They kind of cut through the fluids. Well, the other one we have is called a blunt body. And a blunt body is basically the exact opposite of a streamline because it has a great effect on the fluid. And this is basically everything else. Buildings are a great blunt body. A parachute. You can use this as, if you want to think about it, an Olympic diver that dives into the pool. Very few ripples when they dive. That would be a streamlined body. A great big person that would belly flop into the pool would cause a big, huge splash. That would be a classical blunt body. And so, we can look at it here under those terms. So how are we disturbing the fluid force?